Ladies and gentlemen, thank you for joining us today. Today's symposium is titled Changing How the World Learns. The symposium is hosted by MIT Computer Science and Artificial Intelligence Lab, CSAIL, Quanta Computer, 广达电脑, and Epoch Foundation, 时代基金会. Today we're going to look at how massive online open course platforms, MOOC, are redefining teaching and learning in the 21st century. First, let's welcome Mr. Barry Lam, Chairman of the Epoch Foundation. Mr. Lam, please. Let's welcome Mr. Lam to the stage.
Ladies and gentlemen, welcome. This is my great pleasure to open the symposium. Many of you have been dedicating to reinvent the classroom. Your vision has led us to participate in a revolution to break the limit of time and space, wealth and hierarchy, just to make the high-quality education available for everyone. On behalf of the Epoch Foundation, I would like to extend our gratitude to all speakers who are representing their most updated results and sharing valuable experience in creating and enriching the platform of MOOC, massive open online courses. The emergence of high-quality online courses is driving the transform of education. Later, the keynote will highlight some of the central ideas drive this revolution, followed by 4 short presentations of MIT's recent work on new education technology. At the 2 panels in the afternoon, we will explore the Chinese perspective on 21st century education and how traditional residential education should evolve in this new era. Ladies and gentlemen, thank you for your participation and enjoy the very first feast of launch of the year of 2014. Now, with the core spirit of MOOC, let us start exploring and sharing. Thank you again.
Thank you, Mr. Lam. Now, this is our great honor to have Professor Anant Agarwal, President of edX, for our first keynote presentation. As background, edX is a massive open online course platform founded by MIT and Harvard in May 2012. Professor Agarwal will introduce edX and its current status, as well as provide an outlook on the MOOC platform. Let's welcome Professor Anant Agarwal.
Thank you. Let me do a quick mic check. Can you all hear me? Okay. Thank you. It's my pleasure to be here this morning. Today I'm going to talk about how we can think about education going ahead, starting with what we've seen of education in the past. So education has had many challenges. If you look at virtually all fields known to mankind, whether it's communication, healthcare, automotives, all of these fields have been completely transformed by technology. But education hasn't. Our education system has been largely the same for 500 years. So as technologists, you can think about what tools we've given professors. The most important tool I can think about was given to professors in 1862. Anybody remember that tool? What tool did we give professors in 1862? A piece of chalk. We haven't done much better than that. So what you see here is this is not a rock concert, and this person that you see here is not Miley Cyrus. This is a professor. What you see here is a classroom at the Obafemi Awolowo University in Nigeria. Now, we have all heard of distance education, but if you look at the people way in the back there, that is a longer distance education. So in large parts of the world, there are real challenges to access to education. People don't have access to a good quality education. We also have challenges in terms of education quality. Our education quality has really not improved substantially in hundreds of years, while everything else around us has completely changed. So with edX, when Harvard and MIT launched edX about 2 years ago, our aim was to try to change all of that. So edX is a non-profit venture. It runs like a startup company, but it is non-profit. So edX has a three-part mission. We want to increase access to education. Anybody in the world should have access to an education, and we are focusing on higher education to start, and then also offering high school courses over time. So anybody should have access to education. It is just an absolute basic human right, and we want to try to make that happen. We also want to improve the quality of education. And then third, we also want to do research in how students learn so that we can, again, try to improve how education happens, whether on campus or online. So in today's talk, I'm going to touch on all three of these aspects of providing access to education to anybody in the world, improving quality, and research. Okay, three parts. So one reason that MOOCs, or massive open online courses, have attracted so much attention is the sheer numbers of it. So when we launched our first course on edX about 2 years ago, my colleague, you can see Professor Chris Terman here, he was part of it, and several other colleagues of mine from MIT. We launched the course on edX on circuits and electronics about 2 years ago. And so we thought we would get about maybe 2,000, maybe 1,000, 2,000 students. But when we launched the course, we had 10,000 students sign up in the first hour of launching the course. And then we had, over time, we had 155,000 students who registered to take this MIT hard course. This was not a watered down course, it was a hard course. And in the end, about 7,200 students passed an extremely hard course. The 155,000 is a very big number. So this is bigger than the total number of alumni of MIT in its 150-year history. 7,200 were how many who passed the course. That is also a big number. So in this electronics course, my colleagues and I teach it every semester at MIT in EECS. And we have about 100 odd students every semester. So we would have to teach for 35 years in order to get this many students to pass the course. These are very big, very big numbers. So edX, we're 2 years old now, and we've been trying to make an impact. We're non-profit in the sense that all the revenues that come in go back into the mission. There are no venture capitalists or no private money in the platform. So today, our numbers are we are close to 1.8 million students from every single country in the world. We have over 3 million courses that have been taken by students. And we have about 130 courses on the platform in languages ranging from English to French to Mandarin Chinese and so on. We have a number of institutions on our platform, about 40 institutions offering courses on our platform. So here are the list of institutions that offer courses. So the way it works is that we partner with educational institutions. So for example, some of the best universities in the world are our partners. So from Hong Kong, for example, we have HKUST, and we have HKU as our partners. From mainland China, we have both Tsinghua and Beida as our partners. And here I'll be visiting with many of your universities and inviting them to come and partner with edX as well. So we have some of the best universities in the world, also including MIT, Harvard, Berkeley, from India, IIT Bombay, who are on the platform. So they put their courses as MOOCs on the platform, and students around the world can then take these free courses. So things have really increased dramatically. When we started out, I said we started with one course. This was the circuits and electronics course. And then we expanded very rapidly from there. We went to 7 courses in the fall of 2012. Professor Gutag is here. Professor Gutag launched his course on Introduction to Computer Science and Programming in Python on the course. It was one of the very first few courses on edX. That course attracted about 100,000 students. So about 7 courses in fall of 2012, and then spring of 2013, about 20 courses. And today we have over 130 courses on the platform. So we've been growing extremely rapidly. We've also begun to do work in terms of credentialing. When students take these courses, these MOOCs, what do they get out of it? Of course, they get education. They learn some good stuff. They get to take courses from great professors. So for example, Professor Yu Shinji, he's a professor of electrical engineering at Tsinghua. So he teaches a course on circuits. So you can take, if you're a student anywhere in the world, you can take a great course from Professor Yu Shinji, for example. So there's many such great courses. And we also offer certificates. So a student can take a course for free. They can audit the course. Or second, they can also take a course for an honor code certificate. So if they pass the course, they get a nice little certificate saying that they passed the course. And third is, for a small fee, students can also sign up for a verified certificate. That's a third track. Audit track, honor code certificate track, and third track is verified certificate track. With the verified certificate track, they pay a small fee. We verify their identity, and they get a certificate which says verified on that certificate. And these certificates are given by our university partners with the X label. So for example, if HKUST, Hong Kong University of Science and Technology, gives a certificate for their course, then the student will get a certificate from HKUST X. We also are taking further steps. Students are saying, okay, taking one course is okay, but we want to take full programs of courses, entire disciplines of courses. And so about 6 months ago, in the partnership with MIT, we are piloting X series. X series are sequences of courses. So there's one sequence in Foundations of Computer Science. So the course includes basic courses in programming, courses in digital computer architecture, for example, being taught by Professor Ward and Professor Turman, who are collaborating to create the digital part of the course. And many other professors are teamed up to create a whole program. So this allows students to demonstrate mastery in a discipline, not just one course. And so there's a 7-course sequence in computer science. There are other sequences, one in logistics, one in aeronautical engineering, one in entrepreneurship. And if students pass and get a certificate for each of these courses, they get what is called an X series certificate. And students are very excited. They post these certificates in their resumes, they post them on the LinkedIn profiles. And many of our students are telling us that they've been able to get better jobs when they have been able to list some of these accomplishments in their resume and when they talk about it at their interviews. We also partner with universities to do other exciting things. So the handout that you have, I believe, contains a little brochure. So CSAIL, MIT, in partnership with edX and with MIT Professional Education, is launching a professional education course in big data. So here, it's a 4-week course. You can sign up for the course, and it carries a small fee, but it's a professional education course. It's a short course meant for business executives, educators, C-level executives. They want to learn about big data and how big data might impact their business. So I encourage you to take a look at that course and think about signing up yourselves or team members in your own organizations for that big data course. The MOOCs are free. In other words, massive open online courses. Anybody can go and take a free course. So courses are free and open. In addition, what we at edX did, when we launched edX 2 years ago, we had committed to making our platform open source. And we did that about 7 months ago. We launched OpenEdX. OpenEdX is the open source edX platform where we made available all our source code for free as open source. Hosting scripts, our tools, the authoring platform, the hosting platform, everything was open sourced, and it's called OpenEdX. And so anybody can take OpenEdX code and launch a platform themselves. So a number of countries and institutions have adopted edX. So for example, This is Xuetang X. So Xuetang X is a Chinese platform. This was launched by the Chinese Ministry of Education and Tsinghua University. They created a consortium of universities and launched Xuetang X. So if you go to xuetangx.com, you can take all of these courses in Mandarin Chinese on their platform. Similarly, France launched their platform. So the French Ministry of Education launched FUN, France Université Numérique. They took the Open edX code base and they launched FUN, so in French. Again, that's the same Open edX code base. Stanford, which was building its own platform, launched class.stanford.edu. And that again is the open source edX platform. And if you look down here, you can't quite see it. If you look down here, on their platform, it says powered by Open edX. So really, this is a movement that is spreading around the world as the open source platform being created in Cambridge and by our global partners like Stanford and MIT and Tsinghua, University of Queensland and others is really catching on around the world. Most recently, Queen Rania from Jordan of the Queen Rania Foundation launched EdRock. EdRock stands for School in Arabic, and so they just launched an Arabic Nation platform for the Arab world where all the courses will be in Arabic. We're also talking to about 6 other countries that will be launching nationwide platforms using the edX open source code base. So this has become a very, very powerful and important movement. I was just talking to some of our colleagues from the Ministry of Education in Taiwan, and he mentioned to me that his group, universities, have also taken Open edX, and they're also launching a platform, already launched a platform in Taiwan based on Open edX. So we are really, really excited with all these global partnerships and collaboration as we create a way to move learning forward in a big way. So next, let me talk about what is an online course look like anyway. What does an online course look like? So first of all, I encourage all of you to go up to edx.org, and it's free, it's easy. I would encourage you to go sign up and share it on Facebook and tweet it and Snapchat it and WhatsApp it and whatever else to your friends, and go and try out some of these to see what the experience is like. Nothing like experiencing it. Let me also show you some examples of what an online course looks like. So what you see here is a course. This is a course from Berkeley. It's a artificial intelligence course taught by Professor Peter Obeil and Professor Dan Klein. I believe this is probably the world's best, no, I take on the probably. This is the world's best MOOC on Introduction to Artificial Intelligence. It's a phenomenal course, and I really encourage you to go check it out. So as part of the course, students, there are no lectures in the course. You don't have 1 hour long or 1.5 hour long lectures. We have what are called learning sequences. A learning sequence are interleaved sequences of short video snippets, YouTube-like videos, 2, 3, 4, 5, 6 minute videos, interleaved with interactive exercises. So if you're a student, you watch a short video, 5, 6, 7 minute video, and following that, you get an exercise, you do some homework, some exercises, right following the video. So these make it much more interactive. Now think of this as making education more Socratic, where you learn, you watch videos, and then following that, you ask questions and you engage with the material. So it turns out that this kind of engagement has been known to improve learning outcomes. This is a form of learning called active learning. The very famous paper by Craig and Lockhart in 1972 that was really created the foundations of active learning, where they showed that when students are engaged while learning, learning outcomes will simply get better. Now, there's been a lot of hype around MOOCs. Well, this is a new thing, new invention, and so on and so forth. But papers like this indicate that learning researchers around the world, like Craig and Lockhart and others, really have known about all of these techniques. And what we are doing as MOOC platforms is really taking all that learning and applying technology and making it possible to engage with learning using technology. Okay, so in some sense, we've not invented anything new. We've really popularized what has been known for a long time. And this active learning is one example of how student outcomes can improve. as we move from hour-long lectures to these interleaved sequences of videos and interactive exercises. And the second big aspect of these MOOCs is how they can engage the student through instant feedback. Okay, so one is active learning, second is instant feedback. So with instant feedback, think of it. When you go to a classroom, normally you submit the homework, and if you're lucky, you get a graded homework back 2 weeks later. You've forgotten all about it. With this platform, what you can do is you can submit an answer to a question, and you get instant feedback. And the platform includes a whole number of technologies to provide instant feedback and automatically grade all kinds of problem types. You can grade equations. Professor Thurman and others created a circuit simulator, so you can build circuits and you can grade those. There are a number of other technologies. You can problems with matrices. I'll give you a quick little demo of a problem with chemical equations. So this one is a problem with a chemical equation. So you ask a question, and students can enter the answer, and they get instant feedback. So let me show you a quick little video of that. So a student enters a chemical equation, and they say, oh, check the answer. Oh, they got it wrong. They try it again. They get it wrong again. They try it again, and they learn, and they keep trying till they get it right. So this brings an element of interaction and gamification into the learning process, where the instant feedback is really, really engaging students extremely well. And researchers have also shown that instant feedback can, again, improve learning outcomes. In fact, our students are telling us, so you see this little green check mark here. So students are telling us that they go to bed at night dreaming of that little green check mark. Now, when's the last time we've seen our students dream about homework? So it's this element of gamification where they can keep trying. And they're working a lot harder. They keep trying because of instant feedback, and they just want to get something right. That's why coding is a lot of fun. When you code, you can keep trying till you get the bug, till you debug it and get it right. This instant iteration, this feedback is extremely important. And this has become so important that the green check mark from edX has now reached meme status. So this is a meme that we found on the internet. And so as a professor, you know you've arrived when something that you're engaged with reaches meme status. Okay, so this is a big deal. So this meme talks about when you get the green check mark for all your answers on the first attempt. And so the green check mark and instant feedback is just very important. The third thing I'd like to talk about in our online learning platform is virtual laboratories. So the edX platform, through the contributions of a lot of the open source partners, is very unique in being able to provide virtual labs through simulation. This is unique to the edX platform. So a lot of people had said, oh, you can't do labs online. Okay, for labs, you really have to come to a university. Well, it turns out that there's not many things on earth that you cannot do online. You may just have to wait long enough. I can think of 2 or 3 things, but beyond those, most things you can do online if you're able to put in use technology and build them out. So one example is online labs. And so here I'm going to show you a quick little demo. This is an online lab which was part of a course from Harvard. It was a course called Science of Cooking. And so here I'll show you a simulation-based lab and this was created by, interestingly, folks at MIT, so at CSAIL. So I think the folks involved were students of Chris Thurman and Rob Miller and others that built the simulator, and very interesting collaboration between Harvard and MIT. So the simulation you will see here is a simulator of cooking meat. So in this lab, students will select the kind of meat they want to cook. It's not very clear, but they can select tuna, steak, and then they can create a recipe. Cook it for 5 minutes on this side, cook it for 3 minutes on the other side, and the whole thing runs in simulation, and then they can study it. This is just one example of a simulation-based laboratory, and I'd like to give you a quick little video. So they select the meat, they select the recipe, and now they're going to cook. So now they can look at temperature profiles, and they can study some physics and science. So just to give you an example of how you can use simulation to create these online labs, and really, some of the spectacular work from people like Thurman and Miller and others and their students And we have a number of labs on the platform, in circuits, in physics labs, chemistry labs, biology labs. The list goes on. And I think that's one of the real rich aspects of online learning that can create a very good learning experience. We can also do a large type of other kinds of exercises, as programming exercises. Professor Gutag and his team built ways to grade Python and other programs. Professor Armando Fox from Berkeley created ways to grade Ruby on Rails kinds of programs for software as a service. So just a lot of these automatic graders and simulators that enhance the learning experience. So at this point, let me make a quick transition into from access to education to campus use. So many of these courses on the edX platform would be used on campuses. I'll give you one example. San Jose State University in California took the edX MIT X Circuits course, and they offered it on their campus. They did what is called a flipped class, or a blended class. The students would watch the videos, do the labs and exercises in their homes. Then they would come to class, and in the class, they would interact with the professor, ask questions, and they would also work. This is a real picture from the class. They would work in teams of 3 and solve problems and do mini quizzes and so on. And the preliminary results from this were just spectacularly good. So traditionally in this course, San Jose State University has had a failure rate of 41%. So in previous semesters, previous years, 40 to 41% of the students would fail the course. In this blended class, taught by Professor Khosrow Gadiri, the failure rate fell to 9%. These results are preliminary. And so if this kind of trend continues, this blended class model might be a very, very interesting way for universities to reimagine education on their campuses. So here's some of the grading curves. So the red, green, and purple curves are the grades. The grades are on the x-axis and percentage on the y-axis for the traditional class. And the blue is the grades for the blended class. Notice how a lot of the students from the low grades are now, the whole thing has been pushed up to the higher grades. And one way to think about it is that in the traditional class, we are very rigid. We're inflexible about the program in terms of time, in terms of lectures. But then there's a big distribution of grades, huge distribution of grades. However, if you look at in the blended class, where people can pace themselves and learn at their own time and so on, you are making the learning process flexible. And what we're seeing is that the grades then tend to bunch up and show a smaller variation. So we thought that was a pretty interesting way of looking at it. We've also had the blended experiments at community colleges. This is a blended class. This was Professor Gutag's and Grimson's Introduction to Python Programming course. And then again, very good results. And one important question I've been asked, when professors use a course in their classroom, where the course was created by somebody else, there's been a lot of criticism about what happens to that professor, the professor that teaches the blended class. If they don't lecture, what do they do? And so you just have to talk to professors like Professor Jamie LaRue, who's an assistant professor at Bunker Hill Community College, who used the MIT computer science course. So she says that instead of giving lectures in class, she works with the students one-on-one and has the students do problem sets and so on. And her view is that if not for her presence in the classroom working with the students would not have passed the course. And so she feels that she's not going to be replaced, but she feels that she's doing something different and much, much more connected to students than through lectures. So it's been a really, really good way for professors to think of how they can change what they do in the classroom and not have to give the same old lectures and follow things in the same old practice. So this kind of blended classrooms are happening all over the world. We have about 40 to 50 such blended programs happening all over the world. So these are pictures from a classroom at in Tsinghua University in China. So they took the Berkeley Software as a Service course, and these are real pictures from the classroom. I won't focus on the results, but very quickly, the students liked it, the class evaluations went up, and the results also improved at Tsinghua based on this blended class. The classroom was also changed. Instead of having rows of students sitting in class and the professor lecturing, They put blackboards on all the 4 walls of the classroom and turned the classroom into having small group activities. And there again, very good results. MIT has been doing a lot of work in this area as well, blending the classroom. And in the space of 1.5 years, this whole thing has been going on for a year and a half at MIT, 2,100, which is about half the undergraduates of MIT, are now accessing blended content using the edX platform in one way or another. And one result that I'll point to from the MIT the newspaper that I found was that in the 5th week of the class, students who are not doing well get a warning letter. In the last 2 years, 50 warning letters and 29 warning letters went out. When he used the blended model in the classroom in 2013 fall, only 2 warning letters went out. So we're seeing that we can improve the education quality and outcomes using the blended class in various, in universities and community colleges and so on. And finally, I want to talk about research. So we are gathering a lot of data. So we like to think of edX as a particle accelerator for learning. We are gathering big data for learning. And this is just one example of research done by Philip Guo, who is now a researcher at CSAIL. He looked at video distributions on edX, and we gather all the data, how students interacting with the course, when did they start, when did they stop, how they're engaged, all the data. We have logs of billions of entries that can be analyzed. And one interesting result he found was, how long should videos be? And on the x-axis here, you see video lengths from 3 minutes all the way to 40 minutes. On the y-axis, you see student engagement. Okay, how much time did students spend watching the video, the median time? The red curve is, the blue curve is for students that got certificates, and the red curve is students that did not get the certificates. Notice that the highest engagement was for videos that are about 6 minutes long. So as you go from 2 minutes to 3 minutes to 6 minutes, student engagement increases. But once your videos become longer than 6 or 7 minutes, engagement decreases. And by the time you get to 40-minute videos, shockingly, those are watched for 2 minutes. So finally, let me stop here and leave you with a thought. What will the future university look like? Now, there's some that say, what future university? What future university? But I think as universities, we can think about rethinking how our campuses look. And all universities are thinking about how should we change, how should we adopt technology. And one view that is becoming increasingly interesting is that the next generation classroom will become a blended class where we blend both online technologies and in-person interaction. Maybe we get rid of lectures, no lecture halls, and it'd be more based on interactive spaces where students are learning, watching videos and learning themselves and engaging in more tutorial style interaction with the professors. But this is one way in which the future classroom might look. Thank you.
Thank you, Professor Agarwal.
Thank you.
Next, let us welcome Professor Steve Ward from MIT Computer Science and Artificial Intelligence Lab, CSAIL. Professor Ward will cover the idea of algorithm education, which is the integration of computational thinking into education programs. Let's welcome Professor Steve Ward.
Well, thank you and good morning. I know that the title of this symposium is Changing How the World Learns, and most of the talks that you're going to be hearing today are exactly on that topic. But I'd like to introduce a little bit of a variation. I'd like to convince you that in addition to changing how the world learns, this current revolution that we're going through is actually changing what the world learns to some extent. And again, like Anant, let me go back to sort of some old history. The way we've been administering education for at least hundreds and hundreds of years is that we start out with very young children and we teach them a bunch of core competencies. We teach them something about natural language literacy. We teach them a little bit of math. We teach them a little bit about how the natural world works and some other things. And we teach all of these core competencies simultaneously. And the idea here is that they're kind of self-reinforcing. We use natural language to teach them math, for example, to explain mathematical concepts and to pose problems that are solved. We use the math skills to teach them aspects of science, and so on. So there's this set of very tightly interconnected ideas that we teach more or less simultaneously in the very early stages of education. And then we specialize, okay, depending on what career path students are heading for. They may learn about accounting or construction or engineering or computer science. So computer science is one of these add-on specialties. And even in our current educational systems, computer science is considered to be a specialty. Okay? You go to college and you take computer science courses if you're interested in computer science, and otherwise perhaps you don't get much exposure to the ideas of computer science. Well, there's a growing movement that feels very strongly that some aspects of computer science deserve to be promoted to be among this basic skill set. And the idea is that just like reading and writing and basic math skills, computer science, algorithmic skills, will reinforce the other aspects of education. It's important to be able, for example, to ask questions that involve algorithms and to expect answers to those questions that involve algorithms. And so the idea is that we can actually improve this basic education by including some algorithmic components along with basic reading and writing and simple math and so on. So that's what I am going to talk about for the next few minutes. And I want to, just to clarify things, distinguish this algorithmic education thrust from some other closely related things that will be talked about today and that Anant has already talked about this morning that I'm not focusing on. Okay, the first is the revolution that's going on, and it is changing the world, the kind of thing that Anant talked about in edX, the massive online education. I think that's terribly important, but that's not what I mean by algorithmic education. There is also a kind of an explosion in the interesting set of computer tools that we have for administering education and for learning. So we now have the internet, we have Wikipedia that is a resource that didn't exist a few decades ago, and many, many other tools and environments and so on that we can use to enhance learning. Okay, those are all very valuable, and they're really part of the algorithmic education picture, but they're only a part of it. There's also a big push going on. You can see lots of evidence from websites like coding.org and so on. A lot of pressure to get programming skills taught early to a wide range of students. And those are all laudable. We think those are very important. And they're really part of the algorithmic education movement, but they're by no means the whole movement. What I'm really talking about when I mention algorithmic education is basically a new model of understanding. If we actually look at the ways in which we measure understanding and expect our students to demonstrate understanding of a subject, well, there are a bunch of kind of old ones that have been around for a long time. If you understand something, you can describe it. Maybe you can explain it, explain how it works. Okay? You can answer questions about it, and you can maybe even predict its behavior in circumstances that you haven't directly observed. Okay? These are all standard metrics for understanding, and they are all compatible with the basic language and math skills that we teach students at an early age. Okay? And those are all still valid metrics of understanding. There's an additional metric that has been popular in universities for many years and is becoming popular in the online education world for both economic and pedagogic reasons, and that is the metric that if you really understand something, you're able to teach it to somebody else. Okay? that's a valuable insight, and it requires some kind of interactive mechanism between the teacher and the student, but that's something that is being exploited, and more being exploited. But there's an additional metric that I would like to add to this list, and that is, if you really understand something, you can program it. Okay? If you have the algorithmic skills, you can actually write programs that analyze it or duplicate its behavior, simulate it, whatever. And that model of understanding is one that is becoming increasingly important. Okay, this idea is not original with me, of course. And in fact, it goes back at least a number of decades. An early proponent of what is now often referred to as computational thinking is a guy by the name of Seymour Papert, whose picture is on this slide. Now, Papert was in fact a student of Piaget and is very famous for a number of contributions. He invented a theory of learning called constructionism, and invented a language for teaching programming to children called Logo. Throughout his career, he was interested in early education and its relation to computation and computational thinking. He's often cited in modern literature for his mention in 1997 of this term, computational thinking, which has become really the name of a movement. But his interest in it really goes back much earlier. So there are much earlier citations, one of which is given here on this slide. So there was some scattered interest by Papert and others in this general notion that computation needs to be part of the basic skill set, not of computer scientists, but of everybody. Okay, something that we should be teaching in elementary school and building on throughout the educational process. But it wasn't until 2006 when a computer scientist that many of us at MIT remember fondly by the name of Jeanette Wing. She was a student at MIT for years and got her PhD under Professor Guttag, who's sitting over here. And she wrote a short, very readable 3-page article in the Communications of the ACM that advocated this notion of computational thinking, the idea that computation should be for everybody, that the ability to characterize algorithms in ways that computer scientists characterize them, involving their parallel or their recursive or their deterministic or whatever, okay? Those basic notions are basic and applicable to processes in every domain. In science, in art, in a whole bunch of other domains. And so she pushed very hard on the idea that these basic notions should be part of everybody's education. And that article hit such a resonant chord, first with computer scientists, then with educators, and with a growing community, that it basically caused an explosion of activity. So there was immediately, a lot of people kind of jumped on that bandwagon, and Jeanette Wing's article has launched this movement called computational thinking. And there are, if you Google for it, you'll find hundreds, literally, of books and papers and literature. You'll find websites that are devoted to computational thinking. You'll find centers that have been set up to promote this idea of computational thinking, and all of this is in service of the notion that every human being, every educated human being, should have some understanding of the algorithmic process and the basic constraints and structures that computer scientists are currently comfortable with. So, we're familiar with much of this, of course. All of us recognize that computation and computational thinking has invaded lots of other disciplines. Okay? If we take economics, for example, we know that the role of algorithms in economics has been significant. We have, simulation technologies. We have game theory, a branch of math that was basically invented by a computer scientist and is very heavily based on algorithmic notions. We have things like pricing models like Black-Scholes. We have, algorithmic approaches to doing things like trading, the flash crash shown in that graph being one symptom of it, and so on. Biology, of course, has become an information science. It's just laced with all kinds of computational ideas, interpreting sequences of nucleotides as code and so on, and many, many other such things. A little bit more subtle is the influence of computational thinking on the arts. And there are many, many such influences, too many to name here, but I wanted to observe that it has been, that computer science has been called by many people the science of abstraction. And there have been other people who have called abstraction the science of art. So by some slightly twisted logic, computer science is the grand science of art. And that relationship has been exploited in a number of ways. We're all familiar with sites that serve media like Netflix and Pandora that build sophisticated profiles of people's taste in the arts. Okay, so they can predict what you would like to listen to next or what movie you would like to watch next. And that technology using machine learning and a lot of other computer science ideas has been recently exploited by a number of companies, Epoch being one, that provide services and technologies that allow business leaders to make actual decisions, whether to green light a product based on this kind of profiling. They can actually make some predictions that turn out to be useful in a business sense, useful estimates of the possible success of the product. So, we can talk about computer science, computer thinking, and how it has influenced various revolutionary ideas in the past, even before it was a popular cult, as it is now. Just to point out a couple of my favorites, this guy, anybody recognize him? That's actually James Clerk Maxwell, okay, who took it upon himself to take the results of the time from people like Faraday and Gauss and so on, and try and come up with a concise, complete description of how electric and magnetic waves interact, okay, leading to the famous Maxwell's equations, which are shown there. Of course, in the process of doing this, he found some little inconsistencies and things that bothered him. And so I kind of view what he was doing as kind of a code review. He was trying to clean up what he viewed as lines of code in the algorithm that runs the universe. Okay? And he actually did a pretty good job of this. One of the things he did in order to do this cleaning up, it was known at the time that changing a magnetic field causes an electric field. And just to clean up some little asymmetries and things, he said to himself, well, what if changing an electric field causes a magnetic field as well? And so he kind of experimented with that idea and in fact cleaned up some things, but it led to this loop, okay? A changing magnetic field causes a changing electric field, which in turn causes a changing magnetic field, and so on and so on. And we have this self-perpetuating phenomenon, okay? And he called that electromagnetic waves and computed the rate, this is all very abstract at the time, computed the rate at which these electromagnetic waves would propagate through space. He could compute that from his equations. And eureka, he found that that speed corresponded precisely to the measured speed of light. Okay? That was a big eureka moment in the history of physics. The realization that this phenomena actually existed and it explained light. Light was an electromagnetic wave. Well, here's a more recognizable face, Albert Einstein, and there we can find lots of traces of algorithmic thinking in some of his insights. How, for example, can the speed of light be a constant, okay? There's a very good sort of programming model of this, and there's an inconsistency that this leads to. If you have observers in different frames of reference, traveling at different speeds, watching the same physical phenomenon, okay, that involves propagation of light, how can they both conclude that the speed of light is the same? But the speed of light, this number, is tied to Maxwell's equations. And Albert Einstein wanted to have this code be pure, be the same in every frame of reference. And so in order to salvage the laws of physics, he had to come up with special relativity. Okay, there are various other examples associated with Einstein. The famous discussion of whether God plays dice with the universe, okay? Well, that sounds a little bit like a religious question, but in fact it's an algorithmic issue, okay? The question that he's musing about here is whether the algorithm that runs the universe is a randomized algorithm. And he thought it wasn't. Modern physicists seem to disagree. Almost more interesting is the history of great thinkers who obviously missed the boat because of the lack of the algorithmic insight that our high school students can have today. Okay? This goofy-looking picture is René Descartes, who's one of a number of famous and very, very smart philosophers who were musing about the mind-body problem. And many of us old-timers studied the mind-body problem in philosophy courses and recognized that this was a mystery that stumped some of the smartest people in the history of mankind. Okay? What they're trying to do is kind of reconcile the physical embodiment of the brain with the kind of ephemeral set of thoughts and opinions and so on that characterize us, that establish our identity as individual human beings. And this was just a great, great mystery to Descartes and to Plato and Kant and many, many other smart people. Descartes, of course, came up with his explanation, which involved Cartesian dualism. Basically, there are two universes of stuff. There's real stuff that hurts when you drop it on your foot, and then there is this sort of mental stuff that is more ephemeral. And he generated this picture shown on the right, which was supposed to make it all perfectly clear to the rest of us. It still leaves me a little bit confused. And the problem here was that there are a number of ideas that are readily accessible to us, particularly as computer geeks, that were just unavailable to Descartes and his colleagues. And as a result, if you actually go and try and talk to a 15-year-old high school kid who's steeped in computer culture, who is familiar, uses computers every day and knows the difference between hardware and software, and understands that the detailed structure of the hardware is only very, very indirectly related to the behavior of the program that's running on the hardware, and understands that there's transient state which holds information which goes away when you pull out the plug and has to be resurrected when you restart the computer and so on. Okay, this is not a problem to people familiar with these ideas. Okay, so this problem that has plagued philosophers for hundreds of years is no longer an interesting problem. Okay, so we have changed by this computer thinking. We have changed the set of problems that actually we find interesting. Okay, well, what about computer thinking in education? I need to say a few words about that. After all, this is a symposium on education. There are a lot of things that we can say about computer science in education, both at the university level and at the K through 12 level, and I won't say very many of them, but let me just point to a couple of my favorite examples. One of my favorite examples is a piece of history at MIT that I was close to, as well as were some of my colleagues. And there were a couple of our colleagues, Professors Adler and Sussman, who in the 1980s experimented with the idea that, they were in the electrical engineering and computer science department of MIT, and they explored the idea that the way to teach electrical engineering is by teaching about technology that simulates electrical circuits. Okay? Now, simulators are used every day, and they were even used back then to teach about electronics, but these people had a new wrinkle. They weren't just handing people simulators and having them simulate circuits. They were handing people simulator code and having them actually read and modify and understand the code. Okay? So the whole notion that this approach was built on is if you understand this code, which emulates the behavior of electronic components and electronic circuits, you understand how electronic components and circuits work. Okay, this was an idea that was way ahead of its time. It was too radical for MIT to actually base its EE program on, unfortunately. Maybe it will happen at some point in the future, but it was an interesting experiment. There are many, many other courses that exist today that have elements of this. The one I'll mention is this Princeton Computer Science 126 course, which purports to teach programming, but it does so in the context of a string of examples that are actually examples taken from other domains. Okay? So it basically has the students go through computerized versions of a bunch of sort of traditional laboratory exercises. Okay? They do work on an M-body simulation. They generate fractal art using recursive programming. They do a simulation of a guitar string and listen to how it sounds, so on. All of this using computer technology. They generate plausible natural language text using various degree Markov models, okay? And they actually do a final lab which involves taking a bunch of image data of particles doing Brownian motion and analyzing that image data and using that to estimate Avogadro's number, okay? So these are all the kinds of things that in more traditional courses would be done in, say, wet laboratories using real hardware and flasks and things like that. But they're done here under a computation-based lab. Okay, in K through 12, there are a number of sort of different channels for efforts. There are a lot of people who are coming up with languages and environments for teaching children computer ideas and even programming. One at MIT is called Scratch, and like many of these things, it involves a programming language that is somewhat graphical. You assemble a program by plugging together programming blocks, somewhat like a jigsaw puzzle. There are also a variety of online computer thinking related resources, and one of my favorites is Computer Science Unplugged. I don't know whether anybody is familiar with that site, but that site has the interesting characteristic that it deals with computer science ideas that can be demonstrated without computers. So it uses real things, experiments using crayons and cups and all kinds of stuff that you can use to explore computer science kinds of ideas, but it involves no computing. And finally, there is the primary motivator for young kids, which is games. And games have a bad reputation among many parents and things, but I actually believe that games have an enormous pedagogic value. Okay, many of the games have some slightly strange, sort of physical environments. They simulate some world that students play in. The world of Goo and Minecraft being two examples of these. But in the exploration of these worlds, the students are motivated to sort of understand in an algorithmic sense what the rules of the world is and how to put together algorithms for succeeding in these worlds, and so on. I think that's an enormously powerful set of educational tools. Okay, so just on the off chance that there's anybody in this room who is not convinced that I'm completely crazy yet, I'm going to explore as sort of a computer geek's cosmic view of the world. And I'm going to start by pointing to simulation games, or simulations. For decades there have been things that simulate cities or simulate civilizations. These have been getting more and more sophisticated over the years. Most of you are probably familiar with some of them. Many of them involve simulated people, often called sims. So here are some primitive sims from one of the games. And the sims themselves have a kind of a primitive behavioral model, okay? Sims can be angry, they can be hungry, they can have emotions like lust and envy and things like that. They are very primitive, the model is very primitive, but after all, these things have just evolved for a couple of decades, and we have evolved for 1 billion or more years. So we can sort of forgive them their lack of sophistication. The interesting thought experiment is, imagine these sims evolving for a few more decades, okay? They get more and more sophisticated, and eventually, perhaps these sims will get to the point where they start speculating about the code in the simulation program that has created them, okay? They actually get speculating and maybe even figure out how to hack that code in the universe that they're running in, which is, after all, just a big simulation program. And so there is, if we sort of take things to an extreme, we can ask ourselves, is that actually a plausible model for the state that we find ourselves in as human beings, okay? We are, after all, trying to reverse engineer the aspects of the universe, which could be represented as lines of code, and we have learned a lot about the code that dictates our own characteristics and behavior. And so maybe this sim universe model has something to it. Okay, and if you follow this for very far, you start asking yourself some interesting questions. For example, maybe the Big Bang happened at the time of the last reboot. Okay, maybe the age of the universe, if we had a command shell that talked to this interpreter, would be the running time of our current incarnation of the universe. Okay. Maybe whoever it is who hit Control-Alt-Del that caused this Big Bang, maybe that's the God that some of us pray to, okay? Maybe the prayers are in fact treated as bug requests or bug reports or feature requests, okay? So there's this sort of model that we can look at which kind of puts our existence and the existence of our local universe in a sort of more global context. And there's a variety of ways that we can build on this, which I won't bore you with, okay? Now, all of this may strike you as being a little bit crazy. And frankly, it is a little bit crazy, okay? I'll defend that by making sort of the meta argument that crazy is not always bad, okay? If we actually look at a spectrum that runs from boring to insane, okay, we can agree about that accounting is sort of goes at the boring end of the spectrum, and the idea of being abducted by aliens is probably at the crazy end of the spectrum. Okay, but when we go to the middle of the spectrum, you would think we ought to be able to find some boundary between profound thoughts and crazy thoughts. And as you get closer and closer to this boundary, my argument is you come up with more and more interesting ideas. Most of the really interesting ideas are very close to this boundary. They hug this boundary. So time travel and quantum physics, both of which have been the subject of very extensive learned papers, scholarly papers that very smart people, not all of whom are certifiably crazy, have written, okay, are things that I would put in that interesting category. Okay? So my contention is that in order to equip our students to think creatively, we need to equip them to be thinking around this boundary, which means they have to think some crazy thoughts as well as some profound thoughts. Okay, so one question we can ask, and I don't have very good answers to this, is what do we do? Okay, suppose we all buy into this idea of computational thinking and the need to get it into our educational process. Well, one thing we could say is we could do nothing. Okay, this is happening. It's happening with us or without us, so if we do nothing, it will continue to happen. Okay, the problem with this is that if we really want our children and grandchildren to be on the leading edge of this, we would like to sort of accelerate the rate at which they assimilate computational thinking. Well, the second kind of thing we can do is work at the college level, okay? Have college courses like CS 126 that introduce computer thinking into the curriculum. And one argument that is often made is the college level is really too late. Okay, the hot spot is down back here in the K through 12, and I kind of agree with that. But at least if we teach computer thinking in college, some of those college students will go off and become high school teachers and so on and teach computer thinking to the kids that they teach. But that involves a generational time constant, which may be that is too slow for us. Okay, we can try and grab existing high school teachers and re-educate them to make them more computer savvy. Okay, and that's a good idea. Many people are doing that. There is the worry that once we teach them to be computer savvy, they'll all get jobs at Google, paying 3 times their salary, and no longer become teachers. But in general, what we would like to do is keep fueling the fire with new ideas, tools, and languages. Okay, so I've been rambling for a half an hour, maybe 31 minutes according to the people with the hook that are flashing signals to me. If there's one thing that is sort of the takeaway message from what I've been saying, it's the following, okay? The impact of computers on education is something that's apparent to all of us and is the subject of all of the talks and discussions you'll hear today. Okay? One aspect of the impact is it's changing the way we teach. Okay? The edX talk and the sort of online deployment vehicles are examples of that. Another aspect is that it's changing the tools we have for learning, okay? Changing the mechanism we have for learning. Okay? These are both serious revolutions. They are changing the world, and there's no doubt about it. But I want to remind you that there is a third and more subtle revolution going on, and that is that computers are changing the way we're thinking, okay? And consequently, changing what we teach and what we learn. And I'll stop here. Thank you.
Thank you, Professor Ward.